Hi, welcome to the next review video. So today we're going to review for test 3, number 3. You have a review sheet here. Okay, so for 7.1, we're going to look at problems 3, 6, 11, and 12. Okay, so let's look at number 3. Okay, so for number 3, we want to find the area of the shaded region. So here's the y-axis, and here's the x-axis. This is x equals e to the y. X equals e to the y, not the other way around. Okay. We have y equals 1. We have x equals y squared minus 2. Okay, so we have x equals y squared minus 2. And we have y equals negative 1. That little thing right there, that's y equals negative 1. Now we want to find the area of the shaded region. Well, the shaded region is this. Okay, it's not too bad actually. You just have a right function and a left function. This is the right function. This is the right function. Okay, and the left function is here. This is the left function. And the left function is there. Okay? And so this area, the area of the shaded region, which is denoted by capital A, is the definite integral. We're going to integrate with respect to y. An approximating rectangle is going to be horizontal, which will tell us that we need to differentiate with respect to y, and we're going to have a right function and a left function. We're integrating from the lowest y value, negative 1, to the largest y value, 1, negative 1 to 1. These rectangles are going to sweep across that region. And so the height of the rectangle is the value of the right function, which is e to the y, minus the value of the left function, which is y squared minus 1. And so the height of each approximating rectangle is e to the y, this x value, which is e to the y, minus this x value, which is x squared, y squared minus 1. And you integrate it with respect to y. There we go. And so let's find this definite integral. This is definite integral from negative 1 to 1. Of e to the y minus y squared minus minus 1 is plus 1 dy. So all I did there was really just do minus minus 1 is plus 1. This is now find an antiderivative of the integrand function. That's e to the y minus y cubed over 3 plus y. That's an antiderivative of the integrand. And that's valued from negative 1 to 1. You plug in 1, you get e to the first power minus 1 cubed over 3 plus 1 minus e to the negative 1 minus negative 1 cubed over 3 plus negative 1. So then e plus 2/3 minus it will be negative 1/3 minus 1 negative 4/3. So it's minus e, minus in parentheses, e negative 1, which is 1 over e, minus 4/3. Okay, so 2/3 minus negative 4/3 is 2/3 plus 4/3. That's 6/3, that's 2. So this is e minus 1 over e plus 2. That's the final answer. Okay, so the final answer is that area is e minus 1 over e plus 2. So that's the area of the shade region for number 3. Okay? Okay, next one. Number 6. Number 6. Sketch the region enclosed by the given curves. Decide whether to integrate with respect to x or y, draw a typical approximate rectangle, label its head and width, find the area of the region. Okay, so you have the book there. You have y equals sine x, y equals x, x equals pi over 2, and x equals pi. Okay, so let's draw the region bounded by those four curves. So you have the x-axis, you have the y-axis, and you have sine x. It's from pi over 2 to pi. So, okay, so I'm going to make this bigger. So we're going to go from pi over 2 to pi. So let's make that pi over, let's make sine x from pi over 2 to pi. X equals pi over 2 looks like that. That's the height of the sine function at value 1 there. This is x equals pi. Y equals x. So this point is 1, 1. And so y equal x will go through this point, and that's interesting, the region's over here. This is y equals x. Okay, so y equals x is there. That's the region between your curves. Y equals sine x, y equals x, x equals pi over 2, and x equals pi. Okay, so we're going to draw a typical approximate rectangle. It's going to be a vertical one because, as you can see, the top function and the bottom function stay the same from pi over 2 to pi. So the top function is going to be y equals x, and the bottom function is going to be, this is y equals sine x from pi over 2 to, in that range, right? And so this is going to be the bottom function. You'll see this is at the bottom, that's at the top. So the A here, capital A, the area of that shade region, is the definite integral from the leftmost x value pi over 2 to the rightmost x value pi of the vertical cut A of x dx, the vertical cross section, the area of the vertical cross section A of x. Okay, so this is the definition from pi over 2 to pi, and that area is now going to be the height, the difference, the top function minus the bottom function. That's x minus sine x dx. And so then that's equal to an antiderivative is x squared over 2 plus cosine x from pi over 2 to pi. And that's equal to, you plug in pi, you get pi squared over 2 plus cosine pi minus pi over 2 squared over 2 plus cosine of pi over 2. This is equal to pi squared over 2 plus cosine of pi, which is minus 1. Minus now, that's pi squared over 8. And then it's minus cosine of pi over 2. Cosine of pi over 2 is 0, so it's minus 0. Okay, and so this is the answer. I'm going to combine this and this. So that's 4/8 minus 1/8, that's 3/8. So that's 3/8 pi squared minus 1. And that's the answer. Okay? So the area of that shade region is 3/8 pi squared minus 1. That's number 6. Too good. Okay. Next is number 11. Sketch the region enclosed by the given curves and find its area. So you have y equals 12 minus x squared. Y equals x squared minus 6. Okay, so let's find the area and curve, right? Area enclosed by those two curves. So you have 12 minus x squared, which looks kind of like that. And you have x squared minus 6. That looks kind of like that. Okay, so then you have the area of the region between them. And so I want to know the intersection points of those two graphs. So I'm going to set the two y values equal to each other. And so that means that 12 minus x squared is going to equal to x squared minus 6. That's 2x squared minus 18 is equal to 0. And so that's equal to 2 times x squared minus 9. And so that's equal to 2 times x minus 3 times x plus 3. So either x equals 3 or x equals negative 3. That's when the y values are the same. So when x is 3, you get y is 3. So they intersect at 3, 3. So I'm going to redraw this graph where the graphs line up, match their intersection points. So the intersection points, when x is 3, you get y is 3. You have 3, 3. When x is negative 3, you also get y is equal to 3. Those are the two intersection points of the two graphs. Okay? So 12 minus x squared, I'm going to have up here. Okay? That's the graph of y equals 12 minus x squared. X squared minus 6, I'm going to have, so we're going to have x squared minus 6, and it's going to go up like that. And this is y equals x squared minus 6. And I'm going to write this over here, y equals 12 minus x squared. Okay, now they intersect at these 2 points. Okay, so now to integrate, I'm going to, so you find the area between these 2 curves. You're finding this shaded region here. And so to do that, our approximating rectangles are going to be vertical. Okay, we have vertical approximating rectangles. And the top function is going to be this function. And the bottom function is going to be that function, right? The bottom of the rectangle is for this curve, the top of the rectangle is for that one. And so the area, which is the area of that shaded region, is equal to depth interval from the smallest x value, which is negative 3, to the largest x value, which is 3, a of x dx, which is like vertical, okay, the difference in heights there. And so that's the top value. Oh, sorry, it's not a of x, sorry, just it's the top function minus the bottom function. Okay, so so it's the top function, which is 12 minus x squared, minus the bottom function, which is x squared minus 6. Okay, top minus bottom. So don't use a of x in example 6 here. We just write the top function minus the bottom function. All right, that equals the depth interval from negative 3 to 3. 12 minus negative 6, that's 18. 12 plus 6 is 18, minus 2x squared dx. Okay, so just write a equals the top, whatever the top is minus the bottom, or the right minus the left. Okay, don't write a of x. For area problems, we use a of x for volume. Okay, so this is equal to 18x minus x cubed, evaluated from negative 3 to 3. And so then that's equal to, plug in 3, and you have 54 minus 27. When you plug in x equals 3, minus when you plug in negative 3, you get negative 54 plus 27. Okay. So you're just calculating this, and so you get 27 minus negative 27. That's 54. Okay, that's 54. Okay, and so that's the answer. The answer is 54. The area is 54. Okay, so that's number. So just write it like that. Don't write it like that. Okay, so that's 54. Number 12 for area. finding here. Number 12. Sketch the region enclosed by the given curves and find its area. For 12, it's y equals x squared. And it's y equals 4x minus x squared. Okay, so you have y equals x squared, and then this is the negative of x squared minus 4x. Okay, if you did x minus 2 in parentheses squared, you would x squared minus 4x plus 1. And so x minus 2 in parentheses squared minus 1 is this minus 1, which is x squared minus 4x. So here, x squared minus 4x is the same as x minus 2 squared minus 1. And so the negative of x squared minus 4x is the negative of x minus 2 squared minus 1. And so that's equal to 1 minus x minus 2 squared. And so y equals 4x minus x squared is also equal to 1 minus x minus 2 squared. Okay? And so that'll help us graph it. So x minus 2 squared is just moving y equals x squared to the right by 2. Negating it is flipping it. So if you had y equals x squared, it would look like this, right? And then if you had y equals x minus 2 squared, by transformations of functions, it would look like that. Then if you took y equals negative x minus 2 squared, it would look like that. And then if you had plus 1, it would then look like that. So our final function, that looks like that. So when x is 2, y is 1, that's the top point. When x is 0, you get negative 3. So sometimes it's good to map the graph crosses the y-axis. Okay. 1 minus 1, negative 3. And so, now where do these two graphs intersect? X squared equals 4x minus x squared. You have 2x squared minus 4x is 0. X times 2x minus 4 equals 0. You have x equals 0 and x equals 2. When x equals 0 and x equals we have x minus 2 squared minus 1. Oh, x minus 2 squared is x squared minus 4x plus 4. And so x minus 2 squared minus 4 is equal to that. There's a minus 4 here. And so it's 4 minus x minus 2 squared. Right, so then, so you still get x equals 0 and x equals 2. Okay, for the intersection points. So, but that's not where it crosses the y-axis. When x is 0, y is 0. It crosses the x-axis here. When x equals 2, then you don't get that point. When x equals 2, you get 2 comma 4 for both functions. Okay, so this parabola, this is the topmost point of the parabola, because when x is 2, y is 4. Look at that. So now you're going to just draw this graph like this. This is the graph of y equals 4x minus x squared. All right, so y equals x squared, y equals 4x minus x squared, and that's the area of the region bounded by those two curves. So you want to find the area of that. This was just the plus 4 part here. Okay, so so the area here is equal to a definite interval from, this is x equals 0, that's x equals 2, from 0 to 2. Right, you have an approximating rectangle here. This is the top function. This is the top function. Even though I wrote it down here, it's the part of the curve that's at the top. That's the top function. Okay, this is the bottom function. Okay, so it's a is the definite interval from x equals 0 to x equals 2 of the top function. I labeled it so that way it's easy to, so you don't lose track of it. That's the top function minus the bottom function, dx. Okay, so you find this definite interval. It's definite interval from 0 to 2 of 4x minus x squared minus x squared minus 2x squared dx. And this is equal to 2x squared minus 2/3 x cubed, evaluated from 0 to 2. That's equal to, plugging in 2, you get 2 times 2 squared minus 2/3 times 2 cubed minus plugging in 0. Into here you get 0. And so this is 8 minus 16/3. So 8 minus 16/3 is 8/3. That's the final answer. Okay. 24/3 minus 16/3 is 8/3, and then that's the area. Okay. So the area of that shaded region is 8/3. So that's number 12. Okay, so that's 7.1. So let's go to 7.2. Okay, so the best way to practice calculus is learn calculus just by doing problems. So okay, so 7.2, number 3. So 7.2, number 3. So find the volume solid obtained by rotating the region bounded by the given curves about specified line. Sketch the region solid and a typical disk or washer. Okay, so you have the book. X equals 2 square root of y, x equals 0, x equals 9, sorry, y equals 9, about the y-axis. Okay, so let's do that. So let's graph that function. So x equals 2 root y. If I square both sides, I get x squared equals 4y. That means y is equal to x squared over 4, or 1/4 x squared. So x equals 2 root y is equivalent to y equals 1/4 x squared. So 1/4 x squared looks something like that. This is y equals 1/4 x squared. Actually, so that it's x equals 2 root y. And then from x equals 0, x equals 0, which is the y-axis, and y equals 9, that line there. Okay, so it's this region here. I'm going to take that region bounded by those curves, and I'm going to rotate it about the y-axis. And so I have the mirror image here. Let's draw the rotation. Okay, so that's our three-dimensional object. So a typical washer look like this. Okay, that's our typical washer with the thickness, right? Okay? And so there's the center of the washer, and the radius is the distance from here to here. The radius is the x coordinate of a point on the curve x equals 2 root y. So the volume is equal to the definite integral. And so since the thickness is like this, we're going to integrate with respect to y. So we go from y equals 0 to y equals 9 of a of y dy. Now I'm using the a, okay? A of y is the area of the washer. Okay? So the area of that shade region is a of y. Well, what's a of y? A of y is pi times r squared, where r is the radius of the washer. The radius of the washer is the x coordinate of this point, but x is 2 root y. So this is pi times 2 root y squared. And so that's equal to pi times 4y. This is 4 pi y. Okay, you square 2 root y, it's 2 squared times root y squared. That's 4y. So a of y is 4 pi y. Equals difference from 0 to 9 of 4 pi y dy. This is equal to 4 pi times differential from 0 to 9 of y dy. This is equal to 4 pi times y squared over 2 evaluated from 0 to 9. Okay? Equals 4 pi times, plug in 9 squared over 2 minus 0 squared over 2. And this is equal to 4 pi times 81 over 2 minus 0, which is 81 over 2. All right, 4 over 2 is 2, so you get 162 pi. Okay, that's the final answer. So the volume is 162 pi. Yeah, so drew the bounded region by those 3 curves, rotated about the y-axis, drew the curve, drew the 3-dimensional object, drew a typical washer there. A of y is the area of that washer, calculated to be 4 pi y, plugged into here, and then found the differential, it's 162 pi. Okay, so that's number 3, 7.2. Okay. Next is number 4. Number 4 is we have y equals ln x. We have y equals 1, y equals 2, x equals 0. So the region is bounded by those curves, and it's about the y. We're going to rotate about the y-axis. Okay, so let's do that. So we're going to find the volume after we take the region bounded by these 4 curves and rotate it about the y-axis. So y equals ln x looks like this. Y equals 1 is there. That's y equals 1. Y equals 2 is here. That's y equals 2. Okay, and x equals 0 is the y-axis. That's x equals 0. And so this is the region bounded by those curves. Okay, y equals 1, y equals 2, x equals 0, and y equals ln x. So that shade region is what's bounded. We're going to rotate about the y-axis. And so I'm going to take the mirror image of this. It'll look kind of like that. Okay, I'm going to bring this arrow a little bit more over so I drew. So you rotate this about the y-axis. You rotate this about the y-axis. Okay, now take a typical washer. It'll look like this. Right? That's the washer. Has a little bit of a thickness. The thickness of the washer is vertical, and so we're going to integrate with respect to y. The volume is the definite integral from y equals 1 to y equals 2 of a of y dy, where a of y is the area of our washer here. A of y is the area of that washer. It's a circle, so it's pi r squared. The radius of the washer is the x coordinate of that point. Right? The x coordinate of that point on that graph is the radius. But the x coordinate, well, y equals ln x. So x equals e to the y. So equivalently, an equivalent equation to y equals ln x is x equals e to the y. And so since the radius of the washer is the x coordinate of the point, and x equals e to the y, the radius is e to the y. So the radius of the washer is equal to e to the y. So a of y is equal to pi r squared. And the radius is e to the y. So this is pi times e to the y squared. This is pi times e to the 2y. So a of y, the area of the washer, is e to the 2y. Pi times e to the 2y. Okay, so a of y is pi times e to the 2y. This is equal to differential from 1 to 2 of pi e to the 2y dy. This is equal to pi times differential from 1 to 2 of e to the 2y dy. So I'm going to let u equal 2y. du is equal to 2 dy. I'm missing a 2 here, and so I'm going to put a 2 in front, a 1/2 outside, and a 2 inside. So I put a 2 here and a 1/2 there. 2 dy is du. So that's du. And so this is the integral of pi over 2 times the integral of e to the u du. And so when x is 1, when y is 1, u is 2. When y is 2, u is 4. And so now we have that. This is equal to pi over 2 times the antiderivative, which is e to the u, evaluated from 2 to 4. That's equal to pi over 2 times e to the 4th minus e squared. That's the final answer. Okay? So the volume of that three-dimensional object is pi over 2 times e to the 4th minus e squared. Right, e is the natural number e, which is approximately 2.71828. Okay? That's e. 2.71828. Okay, so that's the first 5 decimal places. Okay, so that's number 4. Next is number 12. Okay, so number 12 in 7.2. Y equals x. Y equals the square root of x. About x equals 10. Okay, so what's the region bounded by those two graphs rotated about x equals 2? So let's take the x-axis and y-axis. Here's the x-axis, here's the y-axis, here's y equals x. This is y equals the square root of x. Okay, so then the origin is 0, 0, and this point is 1, 1. Okay, that's the intersection points of those two graphs. The region bounded by those two graphs is this region here that I'm shading in. Okay, and I'm going to rotate that about x equals 2. This is x equals 1. And so let me extend the x-axis here. Further out, that's the x-axis. So here's x equals 2. That's x equals 2. And I'm going to rotate, I'm going to take the mirror image of that about x equals 2. And I'm going to label y equals the square root of x over here, okay? This is y equals the square root of x. And so I'm going to take the mirror image of it. Okay. So that's the mirror image of that shade region. This is the shade region, but I'm just drawing this mirror image there. Then you rotate it around, and you get this. That's the three-dimensional object, okay? And so for 7.2, we're going to find the volume. And so we use washers for it. So I want to see which 7.2 want me to do. Okay, or okay. So 7.2, we're sticking washers here for this section. So here is a washer. Okay, you're rotating it around the line x equals 2, and you're getting a washer. Right? Here's the middle, here's the center of both circles. Okay, and so the volume is equal to the definite integral. So the washers we're integrating with respect to y because the thickness of the washer is vertical d, right? So we're integrating from 0 to 1, from y equals 0 to y equals 1, and a of y is the area of the washer. So it's differential from 0 to 1 of a of y dy, where a of y is the area of the washer, not the shade region, the area of the washer. Okay? So we just need to find the area of the washer with respect to y and integrate it. Okay, so if we look at a washer here, right? Here's our washer. Here's the center of it. Then what is the radius? Then there's a larger radius and a smaller radius, right? The area of a washer is equal to pi times capital R squared minus pi times little r squared. Where capital R is the radius of the bigger circle, and little r is the radius of the smaller circle. So we need to find capital R and little r. Let's do little r. Little r is the length of this. Right? That's the radius of the smaller circle. Well, the radius of the smaller circle is that. The x-coordinate of this point is this distance. X is y. So that length is y. This whole thing is 2. So 2 minus y is the smaller radius. So little r is equal to 2 minus y. So again, this total distance is 2 because this is x equals 2. This is 2. This is the x distance of a point on the line y equals x. The x distance is y. So that's y. The whole thing is 2. What's left is 2 minus y. That's y. The whole thing is 2. Take this away, and you're left with the radius, and it's 2 minus y. So the radius of the smaller washer, little r, is equal to 2 minus y. Capital R, the radius of the larger washer, is from here to here. This is an x-coordinate on the point y equals the square root of x on the left side, okay? And so the x-coordinate here, so y equals the square root of x, or x equals y squared. We're going to use x equals y squared. So here the x-coordinate of a point on x equals y squared is y squared. This distance is y squared. The whole thing is 2. And so what's left is the larger radius, which is 2 minus y squared. So again, the whole thing is 2. The x-coordinate of a point on this outer circle, is a point on y equals the square root of x. It's equivalently a point on x equals y squared. The x-coordinate is y squared. So the x distance is y squared. So you're taking 2 and subtracting the x-coordinate. 2 minus y squared is the larger radius. So capital R is 2 minus y squared. So capital R is 2 minus y squared, little r is 2 minus y. And so this differential is the difference from 0 to 1 of pi times capital R squared, which is 2 minus y squared squared, minus pi times little r squared, 2 minus y squared, dy. So I just plugged in capital R here and little r here and got that a of y is pi times 2 minus y squared squared minus pi times little r, which is 2 minus y squared. So we're going to calculate this differential. So this is pi times the differential from 0 to 1 of 2 minus y squared squared. That's 4 minus 4y squared plus y to the fourth minus 2 minus y squared, which is 4 minus 4y plus y squared. That's dy. Okay? 2 minus y in parentheses squared is 4 minus 4y plus y squared. And 2 minus y squared squared is 4 minus 4y squared plus 4y to the fourth. Okay, so I'm going to factor out the pi. So I'm just calculating this differential. So this is pi times differential from 0 to 1. 4 minus 4 is gone. Let's do y to the fourth. This is y to the fourth. That's y to the fourth. Negative 4y squared minus y squared. Negative 4y squared minus y squared is minus 5y squared. Then minus negative 4y is plus 4y. dy. Okay, so let's find the difference. So I'm going to continue over here. This is equal to pi times an antiderivative of that function, which is y to the fifth over 5 minus 5/3 y cubed plus 2y squared. Okay, so then if you plug in 0, you get 0. So this is just pi times plugging in 1, because then you just subtract 0. So this is pi times 1/5 minus 5/3 plus 2. Okay, and so that's equal to pi times 3/15 minus 25/15 negative 22/15, 8/15. You get 8/15 here. Okay, so you just add those and subtract that. You get 8/15. So the answer is 8/15 pi. Mathematicians go pencil pushing. Okay, so again, 3/15 minus 25/15 negative 22/15 plus 30/15 is 8/15. Okay, so we have 8/15 pi. So the volume of that three-dimensional object is 8/15 pi using washers. Okay, so that's the last problem that we're going over in 7.2. Let's keep going. So next is 7.3. So 7.3, 5, and 12. Okay, so number 5 in 7.3. So y equals e to the negative x squared. Y equals 0. X equals 0. X equals 1. Okay, cool. Okay, so you have the x-axis and y-axis. So if you have y equals 0, that's the x-axis. X equals 0 is the y-axis. X equals 1. That's x equals 1. So the x-axis, y-axis, x equals 1. E to the negative x squared. So e to the negative x will look like that. E to the x looks like this. E to the negative x looks like that. E to the negative x squared will just decrease and increase faster. So you'll just get a function that looks like that. Pretty much has the same shape as e to the negative x. It just decreases faster here and increases faster here. This is y equals e to the negative x squared. So the region is this one. That's the region bounded by those 4 curves. So for number 5, you're going to rotate about the y-axis. Okay, so this is a blue problem. Okay, so then this point, when x is 0, you get y is 1. Just so do that now. This point here, when x is 1, you get y is 1 over e. Okay, so now take the mirror image of these things. Okay, so now let's rotate it. There we go. Rotate it here. So that's our 3-dimensional object. Okay. Now, in order to find the area, we're going to use cylindrical shells. And so that means let's take just a vertical rectangle, right? A vertical line segment in the shade region. Think of this region being covered by vertical line segments sweeping from the left all the way to the left to the right, where it varies in height depending on the height of e to the negative x squared. Just think of these vertical lines, covering that whole space. For each vertical line, we can rotate that about the y-axis, and when you rotate that vertical line about the y-axis, you'll get a cylindrical shell with some infinitesimal thickness. Okay, delta x. Okay, so if you take each very thin line segment, vertical line segment that covers the entire shade region, you take each of them and rotate each of them separately about the y-axis. Each of them you get a cylindrical shell. And if you consider the space that all those cylindrical shells take up, they take up the entire 3-dimensional space. So just like the vertical lines make up the entire area, entire 2-dimensional space, when you rotate the two-dimensional region around, correspondingly you could rotate each individual vertical line. And the rotations of each vertical line, you'll get lots of cylindrical shells, and those cylindrical shells will add up to the total three-dimensional space. Okay? So we're using cylindrical shells to get the volume. So the method says take the volume as the definite integral from, we're integrating with respect to x because we have a delta x here. So these are vertical cylindrical shells, and so that means we're integrating with respect to x. So we have x equals 0 to x equals 1. X equals 0 to x equals 1, because the y-axis is x equals 0, this line is x equals 1. And the shade region only goes from 0 to 1, x equals 0 to x equals 1, right? X equals 7 is not in the shade region, only from x equals 0 to x equals 1. Okay, and then we're gonna take this is gonna be 2 pi. The circumference is 2 pi x because the radius of the radius of the circle is the x coordinate. So it's 2 pi x times the height, which is the height of the function, e to negative x squared dx. And so we use the formula, and so it's 2 pi r, which is x times the height e to negative x squared. You can't always just go 2 pi x f of x, because like I said, sometimes the radius will be different, sometimes the height is different. Sometimes the height is the difference of two functions. But anyway, 2 pi x is the circumference because the x coordinate of the radius is the x coordinate of this point. 2 pi x, and the height is the height of the function y equals c negative. So 2 pi x h. Okay, so you just find that definite integral. That's 2 pi times the definite integral from 0 to 1 of x e to negative x squared dx. And so we're going to use u substitution. And so to use u substitution, I'm going to let u be negative x squared here. So let u equal negative x squared. Du equals negative 2x dx. So what am I missing here? I have an x dx, I'm missing a negative 2. So I'm going to put the negative 2 there. Actually, I have a 2 here already. So what I'm going to do is I'm going to negate the outside, get negative pi, and then I'm going to bring the 0, then another negative sign inside, and the 2 inside. So I'm going to get e to negative x squared. The 2 I'm going to bring inside, it's going to be 2x dx, but because I multiply the outside by negative 1, I'm going to multiply the inside by negative 1. I get 2x dx there. I already have a 2. What I'm missing then is a negative sign. And so I add a negative sign outside and inside, and now I have negative 2x dx. That's du. So this I can replace with du, and then the u equals x squared, I can replace the negative x, so I can replace the negative x squared with u. This equals to negative pi times definite integral of e to the u du. And when x is 0, you get u is 0. And when x is 1, you get u is negative 1. Okay? Now, I'm going to switch the signs of the limits of integration and get rid of the negative sign. So this is pi times the integral from negative 1 to 0. Get rid of the negative sign, but switch the limits of integration of e to the u to u. And so now, this is pi times e to the u evaluated from negative 1 to 0. Okay? So this is pi times e to the 0 minus e to negative 1. And so this is pi times 1 minus 1 over e. That's the answer. Okay? And so the volume of that three-dimensional object is pi times 1 minus 1 over e. All right? Good. So that's number 5. Let's go to number 12. Okay, so number 12. So 7.3, number 12, we're going to use cylindrical shells again. And we're going to take the region bounded by the following curves and rotate it about the x-axis. Okay, so it's in the book. X equals y, 4y squared minus y cubed. X equals 0. I'm going to rotate about the x-axis. Okay, so here's the y-axis. This is the x-axis. X equals 4y squared minus y cubed. And x equals 0. X equals 0 is the y-axis. Okay. Okay, so when y is 0, x is 0. So the origin is a point on the graph of x equals y squared, y squared. So actually, let's factor out the y squared. We have x equals y squared times 4 minus y. When y is 0, x is 0. When y is 4, x is also 0. When y is 4, 4 minus 4 is 0 here. And so those are the two zeros of x. So that's 0, comma 4. Okay. Okay, so it's going to be going this way, curve. If y was 2, which is in between 0 and 4, if y was 2, then you would get 16, minus 8, you would get 4 for x. I'm sorry, you would get 16 minus 8, which is 8. So x is 2. I'm sorry, when y is 2, x is 8. So 8 comma 2 is the point there. So it's bounded by x equals 0 in that graph, okay? So even if this is not perfect for the graph, what we can see is that the right function throughout this interval is going to be this graph. X equals 4y squared minus y cubed. This is going to be the right function. And the left function is going to be x equals 0. That's the left function. And so we're going to integrate with respect to y. Okay? We're rotating this about the x-axis. Okay, we're rotating about the x-axis. So we're going to take this region, we're going to rotate it about the x-axis, get this. And so cylindrical shell is going to look like this. So that's our cylindrical shell. Okay, so the volume, according to cylindrical shells, is the definite interval from the smallest y value, which is 0, to the largest y value, which is 4. Of 2 pi y is the radius, and then the height, which is the x value, is 4y squared minus y cubed dy. And so now this is equal to 2 pi times differential from 0 to 4 of y times that, which is 4y cubed minus y to the 4th dy. And this is equal to 2 pi times y to the 4th minus y to the 5th over 5. That's the antiderivative of the integrand function. Evaluate from 0 to 4. And that's equal to 2 pi times, plugging in 4, you get 4 to the 4th minus 4 to the 5th over 5, and then minus 0. Okay? And so then that's equal to that minus 0, right? Okay, and so then that's equal to 256. This is 2 pi times 256 minus. So 4 to the 4th is 256. 4 to the 5th is 1024. So it's 1024 divided by 5. Okay, so 4 to the 5th is 2 to the 8th power. 2 to the 10th power, which is 1024. So this is equal to 2 pi times 5 times 256 is 1,280. Let me just check that. 1,280. Yeah, 1,280 minus 1,024, which is 256. So it's 256 over 5. Okay, so that's the same thing as 512 divided by 5 pi. Okay, so the answer is 512 over 5 pi. That's the volume of that three-dimensional object. Okay, so that's by the method of cylindrical shells. Right, so 2 pi y is the circumference, and the height is the x distance, which is 2 pi y, 2 pi r h, 2 pi r circumference times the height, which is the x distance of this graph, which is 4y squared minus 1b. And you integrate, look at that, 512 over 5 pi. So that's number 12. .4, numbers 9 and 29. So 7.4, number 9. Find the exact length of the curve. So for number 9, you have y equals x cubed over 3 plus 1 over 4x. 1 less than or equal to x less than or equal to 2. So we're going to find the exact length of the curve here. So the length of the curve by the arc length formula theorem is, this is the differential from 1 to 2 of the square root of 1 plus f prime of x, or actually I would use Leibniz notation, 1 plus dy dx squared dx. Okay, so if you find that differential, you find the length of the curve of this function, the graph of this function, from x equals 1 to x equals 2. That's a 4. Okay, so dy dx is equal to x squared plus 1/4 x to the negative 2, minus 1/4 x to the negative 2. Oh wait, sorry, I'm taking the derivative. Okay, so this is 1/4 x to negative 1, so it's minus 1/4 x to negative 2. I think this is what I said. All right, so that's the derivative, and then you square it because you're going to do dy dx squared. So dy dx squared is x squared minus 1/4 x to the negative 2 in parentheses squared. That's equal to x to the 4th minus 1/2 plus 1 over 16 x to the negative 4. So dy dx squared is x to the 4th minus 1/2 plus 1/16 x to the negative 4. So this is equal to differential from 1 to 2 of the square root of 1 plus that. 1 plus x to the 4th minus 1/2 plus 1/16 x to the negative 4 dx. And so this is equal to differential from 1 to 2. 1 plus negative 1/2 is positive 1/2. This is x to the 4th plus 1/16 x to the negative 4 plus 1/2 dx. Oh, it's the square root of that. It's differential from 1 to 2, the square root of x to the 4th plus 1/16 x to the negative 4 plus 1/2. So here's the trick. This expression is, you can express this as something squared. And so you see an x to the 4th here. So think of x squared, which is the square root. And you think of 1/16 here as plus. Think of the square root of that, which is plus 1/4 x to the negative 2. So the square root of x to the 4th is x squared. The square root of 1/16 x to the negative 4th is 1/4 x to the negative 2. Now put that in parentheses. X squared plus 1/4 x to the negative 2 and square it. Let's see what you get. When you square it, you get this is equal to x to the 4th plus 1/2 plus 1/16 x to the negative 4. That's what you want. And so what I showed is that x squared plus 1/4 x to the negative 2 squared is equal to x to the 4th plus 1/2 plus 1/16 x to the negative 4. So what's in the square root here, you can write as x squared plus 1 over x to the negative 2 squared. So substitute differential from 1 to 2 of the square root of x squared plus 1/4 x to the negative 2 squared. the square root and square cancel. And so now you're left, now you have the definite integral from 1 to 2 of x squared plus 1/4 x to the negative 2 dx. And this is equal to an antiderivative of the integrand function, which is x cubed over 3 plus minus 1/4 x to the negative 1. Okay, and you evaluate it from 1 to 2. Okay, and so that equals, when you do the arithmetic, you get 8/3. We can do this calculation, 8/3 minus 1/8. So 8/3 minus 1/8 minus 1/3 minus 1/4. This is just calculating this, right? We've done this 7 times. So 8/3 minus negative 1/3 is 8/3 plus 1/3, 9/3, that's 3. Negative 1/8 plus 1/4, negative 1/8 plus 2/4 is, negative 1/8 plus 1/4 is negative 1/8 plus 2/8, which is plus 1/8. So 3 plus 1/8 is 25 over 8. So the answer is that equals 25 over 8. That's the answer. There you go. That part. Okay, so the answer is 25 over 8. The trick is that this expression here, x to the 4th plus 1/16 x to the negative 4 plus 1/2, can be written as x squared plus 1/4 x negative 2 squared. And when you substitute that into there, the square root and square cancel, and now you have a function you can integrate. You can't integrate this at first. You have to rewrite this way so you can get rid of the square root and square, and then you have that. This you can integrate, that you usually can't. Okay, so how did I get this expression, right, from this? Well, take the square root of x to the 4th, you get x squared. Take the square root of 1/16 x to the negative 4, you get 1/4 x to the negative 2. Then take their sum and square it, and you get that. Okay, so in these kind of problems, arc length problems, some of them can be solved with this technique, and some of them you have to use other techniques. Other problems you have to use U substitution. Sometimes you need U substitution. In this case, you use this method. Okay, keep going. Number 29. Okay, so 7.4, number 29. Find the arc length function for the curve y equals 2x to the 3/2 with starting point p naught 1, 2. Find the arc length function. Okay, so the arc length function s of x is equal to the definite integral from the x coordinate of this point, which is 1, to x, of the square root of 1 plus dy dt squared dt. Where you think of here, you think of y as a function of t, so y of t is 2t to the 3/2. Okay, t is our dumb variable. So dy dt, so derive this with respect to t, so that's 3t to the 1/2. And then dy dt squared is equal to 3t to the 1/2 squared, and that's 9t. So dy dt squared is 9t. So this is equal to the definite integral from 1 to x of the square root of 1 plus 9t dt. And now for this, you need to use U substitution like I mentioned last problem here. Let u equal 1 plus 9t. Let u equal 1 plus 9t. du is equal to 9 dt. Put a 9 in front there. You put a 9 here. Let me add a step for that. This is square root from 1 plus 9t from 1 to x. I'm going to add a 9 here, so 90t, and I'm 1/9 on the outside. They cancel out. This is equal to 1/9 definite integral of the square root of u, which is 1 plus 9t, and then 90t is du. But when t is 1, you get u is 10. And when t is x, you get u is 1 plus 9x. Okay? And so this is equal to 1/9, the definite integral from 10 to 1 plus 9x of u to the 1/2 du. This equals to 1/9 times 2/3 u to the 3/2 evaluated from 10 to 1 plus 9x by the evaluation theorem. I just moved the 2/3 out there. And so this is equal to 2 over 27. 1/9 times 2/3 is 2 over 27. Okay, times, plug in 1 plus 9x, you get 1 plus 9x to 3/2 minus 10 to 3/2. That's it. That's the answer. Okay, so s of x, the length of this curve, starting at p naught, which is 1, 2, s of x, the length of the curve, is 2 over 27 times 1 plus 9x to 3/2 minus 10 to 3/2. Okay? Don't try guessing that answer in an exam. I don't think you'll be able to. Okay? So that's s of x. Okay, so 7.4. Okay. Okay, 7.7. Okay, so 7.7 numbers 3 and 9. So let's go to 7.7. Got it. 7.7 numbers 3 and 9. So let's look at number 3. Solve the differential equation. So you have x, y squared, y prime is equal to x plus 1. So x, y squared, y prime is equal to x plus 1. Solve the differential equation. So I'm going to write this in line by substitution. This is dxy times dy dx equals x plus 1. I'm going to keep y here with the dy. I'm going to move the dx the other side and the x. So this is going to be y dy is equal to x plus 1 over x dx. Okay, I move the x to the denominator here, put the dx over here, and put the y there. Now I'm going to integrate both sides. This is y squared over 2 is equal to the integral of 1 plus 1 over x dx. X plus 1 over x is 1 plus 1 over x. This is equal to the integral of 1 plus x to the negative 1 dx. I'm just rewriting 1 over x as x to the negative 1 using exponents instead. An antiderivative of that function is x plus ln x. Okay, so x plus ln x is most general antiderivative plus c. And so what we have is that y squared over 2 is equal to x plus ln of x plus c. And so I'm just going to write that here. Y squared over 2 is equal to x plus ln x plus c. This is solving for y implicitly in terms of x, and that is sufficient for an answer, for a solution to differential equation. Okay, so this is solving for y implicitly in terms of x. All right, this is c is an arbitrary constant there. So that's the answer to number 3, solving differential equation. Let's do number 9. So next is number 9. Okay, so for number 9, we're going to find the solution of the differential equation satisfying initial condition. So for number 9, we have dy dx is equal to x over y. Y of 0 is equal to negative 3. Okay, so cross multiply this, you get y dy equals x dx. We have a separable differential equation, integrate both sides. We get y squared over 2 equals x squared over 2 plus c. Okay? Y of 0 equals negative 3. So when x is 0, y is negative 3. So negative 3 squared over 2 is equal to 0 squared over 2 plus that c. So what does c equal? Well, negative 3 squared is 9. 9 over 2 is equal to 0 plus c. That implies c equals 9 halves. And so the solution to the initial value problem is that you have this difference, you have this general solution, and you use c equals 9 halves. So you get y squared over 2 is equal to x squared over 2 plus 9 halves. That is the solution to this initial value problem, number 9. All right. Okay, so we now solved every problem on the review sheet. We have a little bit more time, so I'll do another one. So let's do number 10 in the same section. So I'm going to add number 10 here to our review. Okay, so number 10. So for number 10, we want to find the solution of the differential equation that satisfies the initial condition. So dy dx is equal to ln x over xy, and y of y equals 2. Find the solution of the differential equation that satisfies the given initial condition. Okay, so I'm going to put I'll put the y's on the left side and the x's on the right side. So you get y dy is equal to ln over x dx. Integrate both sides. The integral of y dy equals the integral of ln of x over x dx. So that integral is easy to compute. This one, we need u substitution. So I'm going to let u equal ln x. du is equal to 1 over x dx. So that means that this equals the integral of, so ln of x is u, and then the x in the denominator is 1 over x dx, and that's du. That equals the integral of u du. So the integral of y dy equals the integral of u du. That means that y squared over 2 is equal to u squared over 2 plus c. And u is ln x. So it's ln x squared over 2 plus c. So we have that y squared over 2 is equal to ln of x squared over 2 plus c. Y squared over 2 equals ln of x squared over 2 plus c. Y of 1 is equal to 2. So when x is 1, y is 2. So 2 squared over 2 is equal to ln of 1 squared over 2 plus c. Okay, so u, I'm just going to rewrite this over here so I remember. I'm going to let u equal ln x du equals 1 over x dx. That was for over here. 2 squared over 2 is 4 over 2. That's 2 equals ln of 1 is 0. That's 0 squared over 2 plus c. That's 0 plus c, that's c. So c is equal to 2. So if c equals 2, this is our general solution, but plugging in c equals 2. So the final answer is y squared over 2 is equal to ln x squared over 2 plus c, which is 2, plus 2. That's the final answer. And that's solved. That's the solution of this initial value problem. This is solved for y implicitly in terms of x. Okay, and so that's a solution to an extra problem. Okay, so hopefully going over these review problems has helped. So you should have done these problems on your own, and so this should just be to make sure you were right or clarify something. Okay, so good luck.